radiation, which is denoted by G. Irradiation is the sum total of all the rate of radiation heat transfer, the rate of radiation heat transfer, radiation incident on the surface on the unit area of the surface. Like if this is the surface, suppose it is receiving heat from the wall or human body or any stone, and let's say tree, all are emitting radiation, means all have some temperature which is non-zero Kelvin, so all will be emitting their radiation. So whatever, all the sum total of all the radiation incident on this surface from all the sources at all the wavelengths, this is the irradiation. It is also in watt per meter square. Say because of irradiation, because it is receiving the heat from all the sources, so its internal energy or thermal energy will rise. Rise when a body receive irradiation. Similarly, if body is emitting, so when body emits radiation, its thermal energy decreases. So when body receive energy, let's say this is the body which is receiving heat from all the sources as G, but it can only absorb some amount of the energy. So what amount of energy it will absorb is decided by the property which is called as absorptivity. So whatever the amount of energy that is absorbed by the body is nothing but alpha times the energy it is receiving. It is absorptivity. If alpha is less than 1 and it is opaque surface like metals, then some portion of the energy which is receiving by it, portion of irradiation are reflected. And opaque bodies don't transmit radiation, they only reflect and absorb. That's it. And for semi-transparent medium, they absorb, they reflect, and they transmit also through them. Transmit radiation. Suppose these are the surfaces. This is opaque surface. And suppose this is a glass surface which is semi-transparent medium. transparent medium. So whatever the amount of energy it will receive as irradiation, some of the amount of energy will be reflected, some amount of energy will be absorbed by this opaque surface, which increases thermal energy, and but there is no transmissibility. Another property, three properties are there: absorptivity, emissivity, transmissivity, and reflectivity. Four properties. So it will, let's say it is also receiving the same amount of radiation G. Some amount of energy will be transmitted, some amount of energy will be transmitted, reflected. This is reflected, transmitted. Tau is also 0 to 1, same as the alpha reflectivity. And emissivity, and some of the energy it will be absorbing, alpha times G. So G is nothing but sum total of reflection, absorption, and transmission. So if we take the G out, then we got reflectivity plus absorptivity plus transmittivity as is equal to 1. It is important relation in radiation speed heat transfer. There is special case which is very predominant in radiation heat transfer, which is most of the time is used. So before that, we have to understand what parameters alpha depend on what parameters alpha or absorptivity depends. So alpha is function of nature of irradiation. And surface on which it is and so nature of irradiation means that if some body is absorbing thermal energy radiation, so that absorptivity depend on the surface itself as well as the nature of irradiation. So for example, sun will the amount of energy that will be absorbed by the surface is different for the sun and different for the furnace wall and different for the tree. Like this surface will have different absorptivity for this tree, for this stone, and for this man. One special case which is predominantly used in convection heat transfer is the small surface kept in small surface at temperature Ts, kept in a much large enclosure. For example, it is seen, for example, you can see here. So this is the small surface. This is the small surface. It is kept in much large enclosure or surrounding. And surrounding is at a constant temperature, means at every point surface is Ts, C surrounding. Okay, and for this surface there is no variation of temperature on the surface, so it is at constant temperature Ts. We are assuming that. And like a small pen or like let's say steam pipe is running in plant, uninsulated steam pipe is kept in large room of a power plant, so these type of cases are considered in this situation. So between enclosure and the surface there is gas, so and gas has some convection, heat transfer coefficient, and its temperature T infinity, and that temperature T infinity, the surrounding gas temperature, must is not necessarily be to be same to T surrounding. They both can be different or both can be same. Yes. So what is the heat transfer from this small surface kept in large enclosure? We have to find that now. So let's say this is the large enclosure at T surrounding, and steam pipe is going inside this large room. So what is the amount of heat transfer from the pipe? And the surface of the pipe is kept at Ts temperature at all points, surface temperature, and air is there, some let's say gas as Ts and H as the parameters. So you have to find the net heat transfer. So total heat transfer from the surface to the surrounding is combination of convection and radiation. Convection we can find by the Newton's law of cooling. Let's say H times Ts surface temperature, sorry this is T infinity, Ts minus T infinity, plus if you know the emissivity of this surface, and let's say and all the surfaces are not black body, so it is epsilon times sigma Ts power 4 minus T surrounding power 4. This is the net heat transfer flux. So this is watt per meter square. If we want to calculate the total heat transfer in watts, then we have to multiply by this. In watts we can find by multiplying the surface area of the pipe by the net heat flux, which is nothing but pi times d times L times the heat flux. That will be in watts. So this is all about the basics and modes of heat transfer. So in the next class onward we will start conduction in detail. Thank you.